All right, today we're talking about inductive and deductive reasoning. So our essential question, what we want to be able to do or answer at the end of this is going to be, how can you use reasoning to solve problems? All right, so what you're going to learn is you're going to learn two things that are going to be called inductive and deductive reasoning. All right, and we'll explain what that is in just a moment. All right, but first we're going to start with some vocabulary. And we're going to start with this one. A blank is an unproven statement based on observations. All right, we're going to call that a conjecture. A conjecture is an unproven statement based on observations. And then we have our next vocabulary word, which we will call inductive reasoning. And we use inductive reasoning when you find a pattern in a specific case. Then we write a conjecture for the general case. So we're going to look at different things, and then we're going to kind of hopefully come up with some kind of pattern. Whether it's something like multiplying the number by 2, or we're adding 1, or something like that. And then we're going to make this general statement that we believe to be true based on the pattern of the different examples that we see. So here's our first example. This is going to be a visual pattern. It has nothing to do with numbers per se, but we're looking for a pattern, and we're going to make a statement based on what we see. Then we want to sketch the fourth figure. So what's the next one going to look like? So if I'm looking at this circle, it looks like it's divided in half. And then this next one looks like I took that half and I divided it in half again. So there was one line here kind of cutting the circle in half. Then this one has two lines cutting them into fourths. This one is going to have three lines cutting them into sixths. So if I'm looking at the fourth one, what looks like it's going to happen is that I'm going to take this and I'm going to cut it using four lines. So here's half, then I got fourth, then I'm going to cut, say, go in this direction and cut it in this way. So then I end up getting, so this would be 1/2, this is 1/4, then I end up getting 1/6. This is going to end up being 1/8. So I would just shade in one of those sections. All right, so I would say each circle is divided into twice as many equal regions as the figure number. So see here, I got figure 1. It's divided into 2 parts. Figure 2 is divided into 4 parts. Figure 3 is divided into 6 parts. So, and then figure 4 would be divided into 8 parts. All right, so if you're writing the conjecture, you would say each circle is divided into twice as many equal regions as the figure number. That would be your conjecture. All right, here's our next example. We'll make a test and conjecture. We have numbers like 3, 4, and 5. These things are called consecutive integers. And we're going to make a conjecture about the sum of any 3 consecutive integers. So looking at these 3 numbers, if I take it and I add 3 plus 4 plus 5, that gives me 12. All right. So now let's look at another set of consecutive numbers. Let's go with 7 plus 8 plus 9. That's going to give me 24. Let's try another one just to kind of see if we can come up with some kind of pattern. Okay, so I'm just taking some random consecutive numbers and looking for a pattern. We can even throw in a simple one. Let's go with 1 plus 2 plus 3. That gives me 6. All right, so we kind of want to look at that and see if there is something that we can come up with that we think is true. All right, now this could be a little tricky. It just depends on how your brain works and what you're thinking and what you're looking at. But I'm going to focus with these middle numbers here. And I'm going to compare it to this sum right here. So if I look at 4 and 12, and then I look at 11 and 33, 2 and 6, 8 and 24, 17, and 51. I'm kind of looking, and it looks like if I take that number and I do say 4 times 3, that gives me 12. If I look at 11 times 3, that gives me 33. And if I do 2 times 3, that gives me 6. 8 times 3 is 24. 17 times 3 would be 51. So it looks like that the sum of these consecutive integers is equal to the product of the middle number and 3. So that would be my conjecture. The sum of any 3 consecutive integers is 3 times the second number. That would be my conjecture. And if we wanted to test it, we could just pick some more numbers and see if that pattern works. And it does say integers. It doesn't say it has to be positive or negative. So we could look at -1 plus 0 plus 1. That ends up giving me 0. But if I look at this middle number here, the 0, and I multiply it by 3, I get 0. So it looks like my conjecture is working. All right, let's look at just another number just to kind of give you that example. 100 plus 101 plus 102. That comes out to 303. And if I look at this middle number, 101 times 3, we get 303. So again, it looks like this conjecture is working. So I would say that yes, my conjecture, the sum of any 3 consecutive integers is equal to 3 times the second number. All right, next we have a key concept or core concept, something that is very important that we see coming up, and students have trouble with this or remembering this. So I kind of highlighted it for you so that you know it's coming up. And a counterexample is just simply a specific case for which the conjecture is false. Now, it doesn't have to be a number. It could be a drawing, just the different patterns that you see. If you can come up with a specific example or a case where it proves the conjecture to be false, then that makes the whole thing, the conjecture, false. The whole statement is false. All right, so we're going to look at an example where the conjecture is false, and I'm going to give you an example of what a counterexample is. So, a student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. He's saying or she's saying the sum of 2 numbers is always more than the greater number. So his example would be, say if I had something like 2 plus 3 is equal to 5. Well, obviously 5 is greater than 3. So the sum of 2 numbers, that would be the 5, is more than the greater number. In that case, that would be the 3. All right. So that looks to be true. And if you tried any other number, say like 20 plus, I don't know, 22, that gives me 44, right? And so 44 would be greater than 22. So again, it looks like this is going to be accurate. However, it says the sum of 2 numbers. It doesn't kind of specify what kind of numbers. So if I did something like, say, -2 plus a -3, that happens to be -5. All right, but -5 is not greater than -2. Right. This would be my sum, and in this case, this would be my greater number because we're talking about these happen to be negative integers. So this would be false. Right. So this whole thing right here would be my counterexample. If I take my 2 numbers, -2 plus -3, that gives me a -5. -5 is not greater than -2. So that would make my conjecture false. All right. Hopefully you're still with me. This next key concept is kind of a big deal. We're going to talk about what actually deductive reasoning is, and that kind of actually branches out into 2 different things. One of them is called the law of detachment. The other is called law of syllogism. Excuse me. All right, and deductive reasoning, we're looking at facts, definitions, things that we know and agree on that they're true, and they have this logical argument, this kind of logical basis. All right. This is different from inductive reasoning, which uses specific examples and patterns. All right, so inductive, we're just looking at observations. Deductive reasoning, we're looking at different facts, definitions. We're using other things that have been accepted as true to come up with this logical argument. All right, and then looking at this law of detachment, that just simply says that if the hypothesis is true, then the conclusion is also true. All right, and then looking at the law of syllogism, I'm looking at two statements where I have an if-then statement where I'm looking at the conclusion. My conclusion in the first statement is the hypothesis of the second statement. Now, if both of these are true, then I can kind of sort of merge these two statements together so that if I have my original hypothesis with my second conclusion here, that connection is also going to be true. And we'll kind of give you an example to kind of illustrate what that means. All right, but first we're going to look at this law of detachment, then we'll kind of go back to the law of syllogism and explain what that means and give you an example. All right, if you have two segments that have the same length, then they are congruent. You know that the distance from BC is equal to the distance from XY. So using the law of detachment, what statement can you make? All right, so looking at this, because BC is equal to XY, and really remember that means the distance from B to C. If I can write, distance from B to C is equal to the distance from X to Y. All right. So because the distance from B to C is equal to the distance from X to Y, satisfies the hypothesis of a true conditional statement, all right, then your conclusion is also true. All right. So if we want to put it as an if-then statement, if BC is equal to XY, then segment BC is congruent to segment XY. Okay, that would be an example of us using the law of detachment. Because our definition of a congruent segment, if you remember back from chapter 1, the definition of congruent segments is if the distances of each segment, if the distances are equal, then the segments are congruent. All right, now here's this next example 5. We're going to use the law of syllogism. Now remember that said that if the conclusion of one statement is the hypothesis of another statement, then we can basically merge the two together. So looking at these two statements, this conclusion right here is the hypothesis of this statement up here. All right. So I'm going to write, because that's the way it is made, the sentences are put together, I can kind of combine those and make a new conditional statement. I can say if x is greater than 5, then x squared is greater than 20. Okay, so if you notice, I'm kind of taking these two uncircled statements or pieces, the P and the Q, or P and R, of these two, and I'm combining it to make a new conditional statement. All right, now let's look at this example B here. If a polygon is regular, then all the angles of the interior of the polygon are congruent. If a polygon is regular, then all its sides are congruent. Okay, for this example in here, notice that what's the same is the hypothesis for both of these. Right? It has to be the hypothesis and the conclusion that have to match. Because it's the hypothesis that's the same in both, I cannot use the law of syllogism to write a conditional statement. All right, next example, I'm going to look at a statement or a question and see if we can use some inductive and deductive reasoning to figure out what the pattern is and make a conjecture from it. So if I take any two integers, and let's say I take 2 times 2, that gives me 4. And let's do another one. Let's do 3 times 2, that gives me 6. and just kind of give me some extra information, or some extra examples to look at. If I take a -2 times a +2, that gives me a -4. And let's look at, say, just throw in a negative times a negative. So let's say if we did -2 times -4, that's going to give me a +8. All right. So if I take any integer, so the product of any even integer and any other integer. So let's say if I take one more, let's do, I don't know, 4 is even, and I take an odd integer, that gives me 12. It looks like I'm getting back another even integer. So my conjecture is going to be an even integer times some other integer. It could be positive, could be negative, could be even or odd. It doesn't matter. It looks like I'm getting another even integer back. Okay, that's my conjecture. Now, so let's let these two be any integer. So in order to kind of prove this, I'm going to let m and n be any integer. All right, we're going to use deductive reasoning to show that this is true. All right, so if I take some integer and I multiply it by 2, so I take 2n, then I know that I'm going to get an even integer. And I know that because any number times 2 is even, or any integer times 2. Okay, you learned that way back when, probably in middle school somewhere. 2 times n is going to be an even integer, equals an even integer. And that would be because any integer times 2 is even. And if we do the same thing with 2 times n times m, that represents the product of an even integer 2n. I know 2n is even because of the statement that we just made on top. And if I multiply it by some other number, any integer, sorry, I'm having trouble writing, any integer m, that also has to be even. All right, so that would be kind of my process for testing a conjecture. This conjecture would be true. All right, the next one example is we're going to compare and find the differences, which is an example of inductive and which is an example of deductive reasoning. So let's look at this first example. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up in the air, it will return to the ground. All right, this would be an example of inductive reasoning, and I'm going to explain why. Yes, we know that there's a law of gravity, but the way this is written, it says, so the next time Monica kicks the ball up in the air, it will return to the ground. So that's us looking at her, watching her kick the ball up and seeing it come back down to the ground. So our next statement, or our thought process, is going to say, well, if she does it again, the same thing is going to happen. All right, but now if we look at example B, all reptiles are cold-blooded, parrots are not cold-blooded, therefore Sue's pet parrot is not a reptile. So that would be an example of kind of logical reasoning. I'm not looking at a specific pattern or sequence of events. I'm taking this statement here, the fact that all reptiles are cold-blooded, and the fact that parrots are not cold-blooded. So I'm taking those two facts and I'm kind of merging them together to make a conclusion. Well, that means that Sue's pet parrot is not a reptile. So that would be an example of deductive reasoning. because I'm using the laws of logic, and I'm using facts about animals. All right, this concludes our notes for 2.2, conditional, or not, excuse me, not conditional, inductive and deductive reasoning.